Morning, everybody. Today we're going to explore the next aspect of stoichiometry, really kind of building on what we did last week. So if you remember last week, we looked at mole ratio, which is really comparing one element or one aspect of a reaction to another. This could be if I have so many moles of one element in that I'm starting with. How many moles of another one are we starting with? Well, the next step is to think about that if I have grams and I want of one component, I want to know how many grams are produced if I know what my reactant is. So if we think about this, we can kind of create what I've done in the past is I like a little word tree. So if I am looking at my starting material, or the starting component doesn't have to be, it doesn't have to be a reactant. It could be the product. Depends on what you're looking at in the question. And then we want to know what our final unit is that we want, the final component that we want to know the quantity of. And that could be in grams, it could be in moles, it could be in liters, it could be in a lot of different things. But we really want to focus on how we're going to get from point A to point B. So if our starting point is in grams, and we want to find grams and as our final for the thing we're looking for, we cannot compare grams to grams, but we can compare moles to moles, and that's what we did with mole ratio. So we're going to, we'll just say, we'll call this A, call this B. We want to get to moles of A, so we can get to moles of B, so we can get from there. So if we think about this, moles, if we're going from grams to moles, we want to use molar mass. When we go from moles of one to moles of the other, we're going to use that molar ratio. And then once we're back from moles, we want to get to grams, or again, we're going to use molar mass. And if it asks, if you're starting with moles, well, you just kind of figure where you're out on this tree and what you need to do. If you are already at moles, well, then you can use molar ratio to get to moles of B, and then molar mass to get to grams. If you are at grams, but you only need to get to moles, you're going to use molar mass and molar ratio, and you're done. It's only when you need to go all the way to grams, you're going to use grams to moles, moles to moles of the one you're looking at, and then to grams. And you can also, maybe you're looking at number of molecules. Pull this over a little bit. Number of molecules of A, I want to get to moles of A, and then moles of B, and then grams. Let's see, maybe we're looking for grams of B. So in this case, we're going to use Avogadro's number. And then we'll use molar ratio as our conversion factor. And then finally, again, now we're back to using molar mass. So let's see how this does in practice. I have here a practice problem. Calculate how many grams of iron can be made from 16 grams of Fe2O3 by following the equation. Fe2O3 plus 3 hydrogen gives me 2 iron and 3 water. So anytime we're doing stoichiometry, the first thing you want to do is make sure you have a balanced equation. This one is provided as balanced, but let's just kind of double check. I have 2 irons here, 2 irons on the product side, 3 oxygens on the reactant side. 3 times 1 gives me 3 oxygens on the product side. 3 times 2 gives me 6 hydrogens on the product, and then 3 times 2 gives me 6 hydrogens on the reactant. So everything's balanced so good we can proceed. So looking at this, how many grams of iron? That's our unknown. So if we're doing that little tree, we'd have grams of Fe down here at the bottom. Can be made from 16 grams of Fe2O3. So our starting, what we know is we have 16.5 grams of Fe2O3, and we want to know how many grams of iron are going to get there. So we have grams, we want to get to moles of Fe2O3, and from there we can go to moles of iron, and then from there grams of iron. So if there's our little kind of tree guiding us, let's do this in dimensional analysis. So we're going to start off, all right, since we always start our dimensional analysis with what we know. We know where we're starting material, our starting point is 16.5 grams of Fe2O3. Now I'm going to not even put numbers in just yet. I want to use just our word, just our just the units. From there, if I have grams of Fe2 on the bottom, on the top here, I'm going to go from grams of Fe2O3. And again, we're using, if I'm going to go from grams to moles, we're using molar mass. And remember, molar mass is always grams per mole. So we're going to have 1 mole Fe2O3 on the top there. We got moles of Fe2O3. Now we can use our molar ratio to get to moles of Fe. So if I have moles of Fe2O3 on top, I'm going to do moles Fe2O3 on the bottom. And then we'll have moles of Fe on the top. And then final step, now we've got moles Fe, we want to use again molar mass to get to grams. So we have moles on top, moles of Fe in the bottom, moles, I'm sorry, that should not be moles, getting ahead of myself. Grams of Fe on the top. So we can count, let's just do our cancel out. So we have grams of Fe2 here, grams here, those cancels. Moles of Fe2O3 here, moles of Fe2O3. We're up here to moles of iron. Moles of iron are going to cancel out. So now let's go back in and start putting in our numbers. So we need to first find out what our molar mass of Fe2O3 is. So looking at, we have 2 iron plus 3 oxygens, and I can do the calculations. Oops. Anyway, putting my calculator gives me 159 point, we'll just round it up to 0.7 grams of Fe2O3, that's iron 3 oxide, for per every mole of iron oxide. To get molar ratio, we go back up to our balanced equation. We look at the coefficients in front of the 2 components we're looking at. We have essentially a 1 in front of Fe2O3, so we're just going to put a 1 there. And we have 2 in front of the iron, which means that every mole of Fe2O3 that is consumed, or part of the consumed during the reaction, is going to produce 2 moles of iron. And then finally we get back to, we can just look this one up straight on our periodic table. Molar mass of iron is 55.8 grams per mole. It's really 845, but that's fine. We plug this into our calculator and we end up with 16.5 divided by 159.7 times 2 times 55.8. And that's really how I plug it into my calculator. Gives us a final answer of 11.53033, something like that. But we look back at our sig figs, we have 1, 2, 3 sig figs here. Molar ratio is a conversion factor, so it has unlimited sig figs. And same with molar masses, have unlimited sig figs. So let's make sure, so we're just going to be limited by our starting material of 16.5, which is 1, 2, 3 sig figs. So we have 1, 2, 3 sig figs. We're going to stop there. So our answer is 11.5 grams of iron. Now you'll notice when I do my dimensional analysis, I added all the units, including the component that's being looked at. And this helps with keeping everything straight. When you get to that molar ratio part, you know which one is on top, which one is on bottom, because I have moles of Fe2O3 over here on top. I know that my Fe2O3 is going to be in the bottom. And that's why I do put all my units in first, including what the actual thing is, not just grams. I actually put grams of Fe2O3, grams of Fe2O3, moles of Fe2O3, moles of Fe2O3, moles of Fe, and then again, moles of Fe, grams of iron. So now I know exactly what everything is, and this helps when we get into one of our another aspect we're going to look at where you're going to have to do this multiple times, and you want to make sure you're actually doing it right. So that's it. That's what we're working on today. Just this gram to gram conversion. Just understand where you're starting from and where you're getting to, and so that you can follow along. I've posted a kind of what I call mole island. It helps you look at where you're starting, where you're going, and then where you're and then how to get there. Doing kind of the same thing that you might find easy, just a little visual aid. Hope this helps, and I will talk to everyone later. Thanks. Bye.